And I must say that this is actually a great initiative that you guys have started actually doing. Uh, and actually, yeah, so doing this online series of talks, lectures, and discussions, which is actually very good. And so try to keep it up. Okay, yeah, so when Nirmal actually asked me to give a talk on some topic, I decided, okay, let's talk about stuff which I'm doing right now. So initially, when Nirmal also asked me to send a title for the talk, I sent a very pretentious title, which is Celestial Holography. But then I later decided that let's not be too pretentious. Let's call it Celestial Amplitudes, which is, I guess, probably a better title for these talks. Okay, yeah. So before I begin, I should say that okay, I don't have to tell you guys to actually sort of feel free to jump in with questions and comments at any point of time you like. It's more important that we have a discussion than I get to the end of where I want to. Okay. Okay. So with that, let's begin. Okay. So what is the basic idea behind what I'm going to talk about? So the basic idea is actually very simple, and it is the following observation, which is just a kinematic observation, and that is the fact that if you look at the Lorentz group in, let's say, d+1 space-time dimensions, then which is basically SOD plus 1 comma 1. Then that is basically the same as the Euclidean conformal group in d-1 dimensions. Okay. So now let's say you are interested in as we will be interested in studying scattering amplitudes. So this kinematic fact between the which says that the Lorentz group in d+1 dimensions is sort of equivalent to the Euclidean conformal group in d-1 dimensions. So that kinematic fact suggests that there should be some relation between d+1 dimensional S matrices and d-1 dimensional CFT correlation functions. Okay. So at least S matrices should exhibit some properties of CFT correlation functions just from this kinematic point of view. Okay. But however, when we usually talk about S matrices, let's say the way we learn about scattering amplitudes, let's say from our favorite quantum field theory books, in that case, the way it is usually formulated is that you use a particular set of asymptotic states in order to describe the S matrix. And these asymptotic states are actually energy momentum eigenstates, right? So this we all know. Now this choice has obvious advantages because it makes space-time translational invariance actually completely manifest. However, this choice of asymptotic states, which are energy momentum eigenstates, that somewhat obscures this underlying conformal invariance. And so then if you want to see this conformal invariance manifestly, then what we seek is an alternative sort of basis to describe the asymptotic states in the S matrix. So then the point is that recently such a construction has been done. So for example, in a very nice series of papers back in 2017, actually Pastarsky, Shao, and Strominger showed, or they basically constructed an explicit actually sort of map, explicit map between the standard momentum space asymptotic states and the new basis of asymptotic states. And which they called the conformal basis of asymptotic states. And we will see in more detail what its definition and properties are explicitly later on. But the point of introducing this basis was that one could show is that when you write the S matrix elements in this basis, then they transform manifestly as correlation functions of quasi-primary operators in some conformal field theory. Okay. And recently people have been giving a name to this putative conformal field theory. And this conformal field theory is nowadays referred to as the celestial conformal field theory. And we will see why that it is called so. Okay, good. So now you may ask that, okay, so what are so why are we interested in doing this? We have been studying scattering amplitudes for a long time, and there is a standard way of studying and there is a standard way of doing things. Even in the modern formulation, where let's say you use your fancy spinor helicity variables and so on. But the point is that even in that case, all of it is done in the standard momentum space. But you may ask that why does one seek this conformal basis where one wants to make this underlying conformal symmetry manifest? So one of the motivations for trying to do this is basically trying to gain some understanding of what we mean by flat space holography, which is to say that if you have so basically in this case what we want to do is that we want to understand how to give a holographic formulation to quantum theories of gravity in asymptotically flat spacetimes. And we all know that there is a way of doing that in the case of ADS spacetimes, and which is the ADS CFT correspondence, and that we understand at some level. But in flat space, things are actually things are more mysterious. And it has been actually sort of conjectured by many authors over the past several years that in this case, whatever be the dual of let's say the quantum theories of gravity in asymptotically flat space, that should be some form of a conformal field theory which lives at the boundaries of the asymptotically flat spacetime. And in that case, that conformal field theory is supposed to live on the celestial sphere at null infinity. And so from that point of view, it is sort of natural to have a set of observables which so basically from that point of view, it is natural to have a set of observables which transform naturally under the action of the conformal group. And so therefore this basis seems to be sort of a stepping stone from where actually within which we can try to develop a formalism for a flat space holography. Okay, so and the second sort of motivation is sort of more practical, and that is the following. So recently, as all of you guys know, is that there has been a very beautiful story that has been unfolding, which relates soft theorems in gauge theories and gravity to certain infinite dimensional asymptotic symmetries. Okay. Now, these asymptotic symmetries often take the form of what are known as current algebras on the celestial sphere. And if you want to study what are the constraints of these current algebra symmetries and so on scattering amplitudes, then it is sort of useful to go to a basis where the conformal symmetry is sort of manifest, and then you can use actually techniques which are known in conformal field theory. You can apply actually those techniques to study about scattering amplitudes. Okay. But in this set of talks, what I want to tell you about will mainly be restricted to 3+1 dimensions. Okay. But more or less all that I say here can be at least in this first talk can all be generalized to the case of higher dimensions. Okay, so are there any questions regarding motivation, philosophy, etc., etc.? Okay, good. So if there are no questions about philosophy, then let's move on. Okay, good. Okay, good. So here's a rough plan for what I want to do actually. So yeah, so basically basically for today I want to keep things rather simple. So I want to tell you about what this conformal basis is for the case of massless particles in 3+1 dimensions. So we will discuss its definition and some of its properties. And so this was basically done by Pastarsky, Shaw, and Strominger, which I will refer to as from now on as PSS, abbreviation for Pastarsky, Shaw, Strominger. And then I will discuss a certain modification of this PSS definition, which is useful for certain purposes, and I will tell you what it is all about. And then once we construct this conformal basis, I will from there we can immediately define what are known as celestial amplitudes, and these will be these objects, and we will see that these objects manifestly resemble CFT correlation functions. Okay, and in the end, we will see some explicit examples which people have computed in the literature so far. Okay, so that's for today. But just to give a teaser for what is to come later on. So then, maybe in the second and third talks, we will discuss this formalism of celestial amplitudes for the case of massive particles. So for today's talk, all of the things that I say will be confined to the case of massless particles. But there are interesting things, interesting and more complicated things which happen for massive particles. Then we will see what are the so then we will see what are called conformal soft theorems. So these are the analogs of the usual soft theorems that one usually studies in quantum field theory. And the point would be that these conformal soft theorems will be interpreted as certain word identities for infinite dimensional symmetries in this putative two-dimensional CFT on the celestial sphere. And so from the soft theorems we will try to understand what the symmetries of these two-dimensional CFTs are. And then we will try to understand some aspects of this conformal field theory. In particular, we will try to see so we will try to see some aspects of the operator product expansion, and we will try to understand how the OP in this celestial conformal field theory is sort of constrained by the various asymptotic symmetries which follow from soft theorems. Okay, so that's the plan. Okay. Okay, so are there any questions about plan? No. Okay. Right. Mm-hmm. Okay. Okay. So basically, so now let's focus on the case of. Okay. So now let's. Okay. So now I'm going to focus on 3+1 on 3+1 space-time dimensions. Okay. And what we want to do. Okay. So first of all, let's start with something simple. So okay, so let us consider some arbitrary 4 vector, some space-time vector, which I labeled here x mu. So you can take that, and then what you can do is that you can define, and let's say you define this matrix, okay, which is capital X, and it is this matrix formed by these components of this vector x mu. Okay, so this you are sort of familiar with if you have studied this all this spinor helicity stuff. This is something which you do there as well. So this x mu or this big matrix X. So this can also be written in this form, sigma alpha alpha dot. Okay. Yeah, so basically you are multiplying this with the Pauli sigma matrix and then just considering this. Okay. So now what one can do is that is that now suppose let us consider an SL2C matrix. So SL2C matrices are basically matrices with complex entries and determinant 1. Okay, and let's act with this SL2C matrix on X. Okay, so if we do that, then it is then this okay. So then any SL2C matrix acts on this big matrix X in the following fashion, right? And from this transformation, it is obvious that you preserve the determinant under this action, and so therefore, what this
Shouldn't
means
it
is
be
that
M
yes,
M inverse?
MM inverse.
MX M inverse, because I mean
Right.
for SL2C the inverse is not the dagger, right? To
For
preserve the
SL2C, inverse
determinant
is
you
not.
would need.
Well, so yeah. Well, to preserve the determinant, actually you don't need the inverse because M dagger also has determinant 1. Yeah. So so you're right that we could use M inverse.
Oh, I see,
But,
I see.
yeah.
Okay, sorry, yeah, right. I was thinking of trace. Yeah, sorry, yeah.
Good. Right. Yeah. So this condition is basically the determinant condition. Okay, right. So then what this means is that this matrix M is basically implementing a Lorentz transformation because it basically keeps the Minkowski line element invariant, right? Or it basically preserves the so it basically preserves the inner product between vectors. Yeah. And then if you write this out in component form, then you basically see that the individual components of this 4 vector, they have some transformation. So x mu's so the new x mu's are some linear combinations of the old x mu's, and then this matrix, which depends on which SL2C matrix you took. So that can be thought of as furnishing a representation of these Lorentz transformations, right? So now one thing is sort of obvious from this definition is that if you take two matrices Mn minus M, then they implement the same Lorentz transformation, right? And so therefore, what one says from this, the statement is that SO3, 1, which is the Lorentz group in 3 plus 1 dimensions, is basically equivalent to SL2C mod Z2. So here this mod Z2 is because of the fact that Mn minus M don't generate independent Lorentz transformations. You sort of have to identify them, and that's this quotient, and SL2C is kind of obvious. Okay. So basically from this from this isomorphism between these groups, we see that the Lorentz group in 3 plus 1 dimensions is basically the same as the 2-dimensional conformal group up to Z2 factors. Okay, so you know that SL2C is basically the 2-dimensional conformal group, right? So now you can actually make this a bit more explicit. So for example, what you can do is that you can construct the generators of the conformal group from the Lorentz generators, and there is a very well known and explicit way of doing it. So let me just sort of briefly remind you how to do that. So what you can do is that you can take the 6 Lorentz generators, which are your rotations and your boosts, and you can collect them as follows. So let's say J1, J2, J3 are the rotations along the 3 spatial axes, and K1, K2, K3 are basically the boosts. Okay, and from the Lorentz algebra, you can very easily convince yourself that this is the algebra which these generators satisfy, right? And now what you can do is that from this you can construct generators of Lorentz so from this you can construct generators of the conformal group, which are basically L0, L1, and L plus minus, L0, L1, and L minus 1. So so then these generators are given by some linear combinations of these rotations and boosts, which are given here, right? And you can check that using this set of commutation relations, you can very easily check that the standard algebra of the conformal group is satisfied by these generators, so that is satisfied by these LMs, and so that which is given here. Okay. So far I have told you only about the holomorphic sort of conformal generators, L0, L1, L minus 1. But in the study of 2D CFTs, we also have the anti-holomorphic generators, which are L0 bar, L bar 1, and L bar minus 1. And so those can also be similarly constructed. And the thing is that in this case, what you can show is that, okay, sorry guys, just give me 1 second. I will come back. The lights go off automatically at 7. I have to switch them on. Okay, anyway, so as I was saying, that you can also construct the anti-holomorphic generators. And the anti-holomorphic generators in this case are given as follows. So L bar n is basically given by minus of L dagger n. So this minus sign is a bit funny here. Usually in 2D CFTs, this minus sign is not there actually. But what it turns out is that in this case, basically, so basically in this case, since since these Lorentz transformations are implemented by some unitary operators acting on, which will act on states and so on. So the and so that unitarity, what you can show is that basically that unitarity sort of requires you to impose this sort of funny hermiticity condition, but which is slightly non-standard from the point of view of 2D CFTs. Okay, so so basically that was basically the conformal sort of generators, or the global conformal generators, which you can write down from just the Lorentz generators.
Sudip, will you get Virasoro eventually, or this is all?
No, so as of yet, we don't have Virasoro. So basically this is just a rewriting of the conformal, of the global conformal.
Right, yeah. So what I mean is, in this whole celestial CFT thing.
Good. Good question. So we will come to that a bit later actually. So maybe we will come to that tomorrow. But to answer your question, the point is that there is a conjecture that this putative two-dimensional celestial CFT is not just invariant under the global conformal group, but the entire Virasoro group. And that basically comes from the subleading soft graviton theorem. So you may know this, that sometime back Strominger and collaborators showed that using the subleading soft graviton theorem, you can construct an operator whose insertion in the S matrix basically gives you gives you something which looks like the word identity into the CFTs, which is satisfied by the stress tensor. So from that, one expects that eventually this CFT will have the full Virasoro symmetry.
Okay, thank you.
Okay, good. Great. So we have done enough of group theory. So now let's get to our object of interest, which is the scattering amplitude. Okay. So say suppose we are interested in the scattering of massless particles in 3+1 dimensions. So here I have written the scattering amplitude abstractly in this form. It is basically some overlap between some ingoing state and some outgoing state. So the ingoing state is characterized by some bunch of momentas, P1 to Pm, and the corresponding helicities, which I have written here as sigma i's. And correspondingly, the out states will have some bunch of momentas and some bunch of helicities. Okay. So now, yeah, and in all of these cases, so these momentas are on shell and they are null. So therefore, pi squares are all 0. Okay. So yeah, so what we can, okay, so now let's consider a certain parameterization of this null momenta, which will be useful in what we do next. So what you can show is that you can always parameterize on shell null momenta in the following fashion. Okay, where this omega is basically the energy of the particle, and the z and z bars are basically some complex numbers. Okay. Right. So in this case, this parameterization you can always do. You can easily check that is that this satisfies p square equal to 0. Okay. But now what you can ask is that how does the Lorentz group act on this vector p mu when once you have parameterized it in this fashion. Okay. So now from the discussion which we had a couple of pages ago, so from there we know how Lorentz transformations act in the form of SL to C. And what you can check, this is a very simple exercise. What you can check is that the SL to C matrices, right? So for example, you take some SL to C matrix A, B, C, D. You form let's say this big matrix P mu, which is given by P0 minus P3. Okay, sorry, let me write it properly. So yeah, so you form this big matrix P0 minus P3, P1 plus I, P2, P1 minus I, P2, and P0 plus P3. Okay. And then you can act on this big matrix P with this SL to C matrix in the form that we talked about just a while ago. And then from there you can try to see how these omegas Z and Z bars transform under this action. And so from there, what you can show is that omega and Z and Z bar, they transform in this fashion. Okay. So from this, okay, so now you immediately recognize from this transformation of Z and Z bar that this is basically the Mobius transformation, right? And this transformation, so this is basically the Mobius transformation, or in other words, just the global SL to C transformation. So which we read about in the standard discussion of two-dimensional in the standard discussion of two-dimensional conformal symmetries, right? So now this Z and Z bars, so which entered into the parameterization of the null momenta, they have a nice geometric interpretation. So these objects, they parameterize the space of null momentum directions, which is to say that you basically see from this definition is that Z and Z bar are basically telling you about the direction in which a null vector is pointing at, right? And so if you take the space of all Z and Z bars, then the space that you get is basically the space of null momentum directions. And that has a name. The space of null momentum directions is basically what is known as the celestial sphere. Okay. So so maybe diagram will help. So this is my very poor attempt at drawing, at making a diagram. So basically, in this case, we have the Penrose diagram of Minkowski spacetime. So imagine that there is some scattering of massless particles which is happening. So there are some incoming particles, there are some outgoing particles, and they undergo some non-trivial scattering in the middle of the space-time somewhere. And so since these are massless particles, they start out from in this case, yeah. So they start out in this case from past null infinity, which is denoted as chi minus, and eventually they will end up at chi plus, which is future null infinity. Okay. And so these z and z bars can be thought of as as basically stereographic coordinates on this celestia, on this sphere at infinity. So for example, if you take a space-like cross section of this null cone, which is here, right, or this null cone. So if you take a space-like cross section of this, then yeah, so so basically in that case, every point on that spatial slice will be a sphere. And you can think of z and z bar as being actually stereographic coordinates on that as being stereographic coordinates for that sphere. Okay. Yeah. So you know that chi plus minus is basically topologically equivalent to just a line times S2, and this z and z bar can be thought of as stereographic coordinates on this S2. Okay. And hence, yeah, and that's also, yeah, and so that is how also we see a geometric connection to the celestial sphere, which yeah, which is a space-like cross section of null infinity in Minkowski spacetime. Okay, good. So any questions?
Sudip,
yeah.
This omega is the energy of the modes that reach the null infinity.
Yes, right.
Okay.
Omega is energy of the particle.
It's P0 plus P3 by 2, something like that.
That's right.
Oh, okay.
Yes.
Sudeep, I have a question. So at each U at null infinity, there is a one celestial sphere, right?
Yeah.
And
yeah,
so
right.
so particles with different energy will hit different points at U at like different celestial sphere.
Yeah, so that is right. Yeah, so basically particles, so in this case, so the point is that particles with different energies will end up in this case at different values of z and z bar.
So different values of z and z bar and different values of U as well, right? So suppose if
and different, so in general they could land up at different values of U. Yes, right. Yeah.
Okay, all right, thanks.
Okay, good. Right. Okay, so if there are no more further questions on this, let's move on. Okay, so now what I want to consider. Yeah, go on.
Small question. I thought U goes from minus infinity to plus infinity, right?
U goes from minus infinity to plus infinity.
But omega is greater than 0, right?
Omega is
energy
that is true. That is true.
So isn't there a mismatch of the matching or?
No, mismatch between what?
No, you said that, I mean, the previous question, with respect to the previous question, you said that is it is there like a double counting or?
No, so no. So in this case, there is no double counting. I mean, for example, the point is that so in this case, okay, so maybe the example of a free massless particle will help. So if you just take a free massless particle, then the point is that whatever be its energy, it will ultimately you can associate a direction of okay, so for massless particles it makes sense to talk about a direction of motion, and that direction is basically parameterized by this z and z bar. And so massless particle starts out at some and the point is that suppose you start out at, okay, so for a free massless particle, what will happen is that if it starts out at chi minus, then in that case so then in that case, if it's a free particle, so in that case it just follows a 45-degree line, and if it starts out from some value of uz z bar, here, and then it will correspondingly land up on some UZZ bar here. Yeah.
Right.
Yeah. So massless particles enter and exit sort of at the same point on the sphere.
Okay, so sorry, I have this doubt.
Yeah, sure,
So
go.
what does U represent for massless particle? Like if I have
Yeah.
some, say,
Yeah.
particle at different U's, what does that mean? If the direction is given by ZZ bar, but particle at different U, what does that mean?
Yeah. So that so basically for massless particles, so the point is that for massless particles, the U does not really matter so much in the sense, so in the sense that if you give me a massless particle, then I can uniquely tell you, so then there is a canonical way of associating a direction of motion to it, right. And then that direction of motion is basically parameterized by Z and Z bar. But the U does not really play actually much of a role in that. So what you can, so basically what you can do is that once you reach a particular point on the celestial sphere, you can move the celestial sphere up and down along null infinity. If you translate, so in that case, if you translate by this retarded time coordinate on Scri plus, then you basically move the celestial sphere up and down. But the point is that the massless particle always sort of reaches a particular point on the sphere.
Hello, is U like the retarded time at which the particle reaches the null infinity, right? Like is it true or?
Yeah. So basically, U is the retarded time.
Okay.
So in this case, it will depend. I mean, whether it is so it is retarded or advanced depending on where you're taking this on Scri plus or Scri minus. But yeah. Yes.
Thanks.
Sudeep, I just want to. Can you hear me?
Yeah.
Yeah. So I just want to check that this intuition is correct. Is correct. Maybe it's wrong. So my understanding was that roughly in the way that position and momentum are like conjugate Fourier conjugate variables.
Right.
In the same way, the U coordinate and the particle's energy are like conjugate variables, right?
Yeah. So that so basically, as we will see, so that is actually not correct. So
I see.
So actually we will see an example of that.
Okay, all right, cool.
I mean, in this case, so basically it will turn out that the conjugate of this energy variable is basically the eigenvalue under boosts. So so that will be the sort of conjugate variable.
I see. Okay.
I mean, just on the same lines of what Madhu asked, I mean, my understanding was that you don't have, when you say a particle, it's not localized at a particular U. It's a plane wave, right? So it's highly delocalized in U. It has a precise Z and Z bar, but all particles hit on the same celestial sphere. This was there's only one celestial sphere, basically.
Yeah, right. Yes. Yeah, right. Yeah, yes. You're right. Great. So thanks for the comments.
Sudip,
yep.
But if we have like if we have our usual plane wave basis in which we are expanding the field, right?
Yes.
Then you would have this e to the power I omega u times something else, right? For these modes.
Yes.
So in that sense, is it not like the canonically conjugate variable? Because that's how.
Yes. Well, you could say that, but the point is that, as we will see, that is not actually perhaps not the best way to think about it. Actually.
I see. Okay. All right. Okay. Yeah. Okay.
Okay. Good. Okay. Great. So let's So let's continue. Okay. So now let's talk about, since we are talking about this matrix, let's talk about first of all, let's talk about single particle states. Okay. And from this, everything can be built up because you know that in, at least when you are considering, let's say, this matrix, then the asymptotic incoming and outgoing states are basically non-interacting free states, and then the asymptotic states are just you can just build up whatever the asymptotic state is by just taking the direct product of single particle states, right? So now, so now in the standard form, let's denote single particle states as something like this: P and sigma, denoted by their momentum and the helicity variable. Or equivalently, since we are using this parametrization omega z and z bar, so let's we can alternatively or equivalently we can use a different notation, which I will use from now on, which is this omega z bar sigma. So now you know that under Poincare transformations, these single particle states for massless particles have a simple transformation. So for example, under Lorentz transformations, it just, so basically under Lorentz transformations, it changes in the following fashion. So it basically acquires, a phase, which is basically the little group scaling. And then the momenta gets transformed to some other value. But in this case, the helicity does not change. And under translations, these are of course eigenstates of translation. And so the action of translations in this case is obviously very simple. So now what we are going to do, we are going to, so our goal would be to construct a set of a basis of one particle states, which transforms as conformal primaries do in 2D CFTs with some weights h and h bar. Okay, and we will see in this case if there are any restrictions on this h and h bar. Okay. So in this case, that is what we want to do. So there was a question.
So what are Z and Z bar to be interpreted in the CFT, the cross ratio?
Yeah, so basically Z and Z bar can be thought of as the insertion points of the local operators, which will be dual to this asymptotic states, which will be dual to this single particle states. Okay. So so Z and Z bar are just the coordinates of the operator.
Okay. Sorry.
Yes. So basically we want to construct this basis, and the point is that we want, and then the point is that under Lorentz transformations, which is implemented by some unitary operator acting on the single particle states in the Hilbert space. So we want so what we desired is that these states have a transformation property which looks like this. Okay, and this transformation property is basically the same. Is basically what so this transformation property is basically how two-dimensional conformal primaries transform under the action of the global conformal group. Okay. So then the point is that if we can construct such a basis of states, then this underlying SL2C and write the S matrix in this basis of states, then of course by construction the S matrix will transform as a correlator of primary operators in some 2D CFT. Okay, so that's our goal. Right. So now, so now actually let's, so now before going on, let me point out something which will sort of give us some intuition about the answer, which I'm going to write down in a second. So now okay, so now let's notice that if you take this SL2C representation of the Lorentz group, and consider, let's say, boosts around, let's say one of the directions, let's say the third spatial direction. So if you consider a boost along the third spatial direction with some rapidity, let's say chi, then the SL2C representation of this boost is given by some 2 by 2 matrix, which takes the following form. Okay. Okay, and in this case, the sky is, and in this case, the sky is the rapidity. Okay, but now but now if you stare at this, but now if you stare at this SL2C matrix, actually for a second, then from this it is immediately obvious that in the two-dimensional picture, this basically implements actually scale transformations, right? Because if you act with this SL2C matrix on ZZ bars, then what happens is that Z basically transforms to e to the power chi times Z, right? And similarly for Z bar. So then what this matrix, okay, so then the point is that boosts are equivalent to, so the statement is that boosts are equivalent to dilatations in this two-dimensional language. And therefore from that we infer that if we are looking for a basis in which has some definite conformal weights, then we better look at eigenstates of boosts, right? So what we should do is that we should look for eigenstates of boosts rather than actually working with eigenstates. So rather than eigenstates of the energy momentum. And if we do that, then such a basis will, by construction, will have definite conformal weights. And so that's the first thing that we want. Okay. Good. Okay. So then the point is that So then the point is that how do we then construct? So then the point is that how do we construct our actually kind of boost eigenstates? So obviously, if you take a standard momentum vector, then if you do a boost on it, then of course energy is going to change, right? So then of course we can't work with energy momentum eigens. So then the point is that energy state which is an eigenstate of the energy momentum or space-time translations is of course not an eigenstate of boosts. But what you can do is that you can go to a basis which diagonalizes this boost generator, and that basis is basically implemented by doing a Mellin transform. Okay, so what we do here is that we can define this new basis of states HH bar ZZ bar as being given by an integral transform of the following form. And this integral transform has a name, and it is called the Mellin transform. Okay, so so here I've introduced a Mellin variable, which is this delta, and this Mellin variable delta is related to this HN is related to this HNH bars in the following fashion. So then we see that this helicity, which was sigma, can be interpreted as a two-dimensional spin of the dual conformal primary operator, right? And this I'm sure you are familiar with, that this is the standard form. So this is the standard form for the left and right actually scaling weights, which are related to the dimension and the spin in this fashion.
Sudip?
Yeah.
So I want to ask, so you've written the definition of the new states in terms of the Mellin transform. So maybe you can tell us a little bit about how we know that this is the correct object that, does the diagonalizes the boost.
Yes. So in this case, what I will show in just a few seconds is that So basically, as I showed here, that the transformation property that you want of these states is basically the following, right? So what I'm going to do now is that I'm going to show how to derive that these states, which are now given by a Mellin transform, actually have this transformation property. And so in doing that, we will see that these are actually boost eigenstates.
I hope that this demonstration will sort of what I'm trying to say is that actually, maybe I'll just wait until you show it, and then maybe I'll ask my question after that.
Okay, sure. Okay, good. Okay, good. So we have this new definition of states. So this is what was done by Pastarsky, Schrominger, and Shao. Although if you read their papers, PSS did not actually write it in this form. So this particular way of writing it in terms of single particle states was actually done in a very nice paper by Shamik Banerjee. Yeah, so actually I will send you guys a detailed list of references actually. Yeah, so that I will try to do sometime. But just wanted to point at this out.
Sudip, I have a question. Okay, so it may be a naive question, but we have defined a new state here, right?
Yes.
So in the initial state, your state was labeled by three things. It was sigma, sigma delta, and this W. This is the energy, right?
That's right.
So now the new state is, I just see there are like only two labels, H and H bar. So will there be
no? But this Z and Z bars are also there, right?
Yeah, but so Z and Z bar was before else also. But will there be a new? So what happened to the missing label? Like, does it come in some other form?
No.
Or
So
like,
in this case, there is nothing
what's
missing.
happening?
Yeah. So okay. So this might have been a bit confusing and this notation. But what we are doing is that in the ordinary case we had this label, right? We had omega, Z bar, and sigma, right? Okay. And then we are just trading this. And so in this case, we are just trading this set of numbers for this set of numbers. Or what we are doing is that we are trading omega for some delta and Z bar. Okay. So yeah. So in that sense, the numbers match. We are just trading omega for delta. And in this sense, you can think of delta as being the conjugate to omega. So it is basically the Mellin conjugate of omega.
Oh, okay. Yeah.
Is that clear?
Yeah.
Okay, good. Yeah.
So jumping ahead a bit, so this Mellin transformation relation that you just showed between these massless amplitudes and these guys, do they also hold for massive theories? Can I also use Mellin transform to go to this?
No.
States?
So yeah. So good. So good question. So for massive particles, things are a bit more complicated. So for massive particles, the first immediate complication that you can imagine is that basically there is no canonical way of saying what is the direction of motion of a massive particle, right? I mean, because you can always go to a frame where the massive particle is not moving, right? So in that sense, there is no canonical way of associating the trajectory of a massive particle to some unique set of points, actually Z bar on the celestial sphere. And so therefore what you have to do is that you have to integrate over all the directions of the massive particle, right? So in that case, what happens is that in that case also, one can define a new set of states which also live on the celestial sphere, and they are related by an integral transform to the standard sort of Fock space sort of basis states. But in that case, what happens is that the integral transform is a bit more complicated, and instead of this simple factors of and in terms of the simple factors of omegas and all, you get basically what is known as the bulk to boundary propagator. So actually in the next series, so basically I think in lecture 2 we will sort of try to go over the massive case in some more detail. But just to answer your question now, that the case of massive particles is actually is more complicated than this, and it is not given by a Mellin transform.
So for massless particle, it will not be a bulk to boundary propagator, is it?
Yeah. So So for massless particles, basically you can show that this. Okay, so basically, if you start with this ball to boundary propagator for in which appears in the definition of the massive particle, and then you take the massless limit of that, then from that you basically get this Mellin transform. Yeah, so in this case, basically that is how actually PSS sort of motivated this Mellin transform actually. So they first considered the massive case, and when they took the massless limit, they saw that this basis change from this Fox space to this conformal basis is basically given by an integral transform.
Sorry, Steve, maybe this is a naive question, but then if in taking this limit, the massless limit, I would expect that one has to be very careful about it because the particles end up at different places and the Green's functions are different. If you don't want to talk about this now, you want to talk about it later, that's also fine. But I just wanted to register that. Maybe ask you to elaborate on it.
So actually that is a very good point actually. And as you just observed, so basically taking the massless limit of the massive case has to be done very carefully, and in that case what you get. So for example, if you take what is called this massive conformal primary, and if you take the massless limit of it, then what you end up with is that you end up with a massless conformal primary and plus actually a shadow transform of it, where the shadow transform is the usual shadow transform that we talk about in CFTs.
I see.
Yeah. So yes, so the massless limit is actually a bit subtle. Yeah. Okay, good. So thanks guys for all the questions. Very good. Okay, great. So we now have our new states. Okay, so before we go on to check what the Lorentz transformation properties of these states are, let us first check what basically the inner product of these guys are. Okay. So basically, let's compute what the overlap of these conformal basis states are. Okay. So that you basically take the definition, plug it in, and this is what you get. Okay. So you have to do these integrals over these two energies, and you have the inner product between the standard Fox space states. Okay. And this we know. We know that the standard the standard overlap between single particle states takes some formula like this, right? So notice here that I am actually choosing a convention in which the helicity of the particle is defined to be positive if the particle is outgoing, and so therefore you get this, therefore you get this Kronecker delta, where you have delta sigma 1 comma minus of sigma 2, and yeah, so that's just because of the convention I'm working. But this is the standard inner product between massless single particle states. So if you take this definition, you rewrite it in terms of this omega z bar sort of variables. Then you plug it in, and and you also have this three-dimensional delta function. If you write that in terms of this omega z bar variables, that takes some form like this. Okay, and and then and then you can basically plug that into this integral and basically just do this integral. So from there, at the end of the day, so you have to massage this delta functions a bit. There is so it is not a very difficult calculation, but you have to compute some Jacobians and all, which I'm not going to show here explicitly. But maybe this is an exercise to actually show what form this takes. Okay, but anyway, so at the end of the day, if you manipulate the delta functions and compute their Jacobians, blah blah, and so on, then finally the inner product basically takes yeah, so basically that takes this form. Okay, where you are basically left with an integral over one of the energies. So for example, from here you see that you can do one of the energy integrals using one of these delta functions, and the other delta function just actually boils down to this, which is this delta 2 of z1 minus z2. So now this delta function is very easy to interpret, because this delta function just says is that if you have a free massless particle, then a free massless particle enters and exits at the same point on the celestial sphere, right? So that is the interpretation of this delta function. But then you have an integral over one of the energies which is still left. So I have done some relabeling of variables. So this can either be omega1 or omega2, but I have changed integration variables to call this just omega. But if you compute this, then you will find that this has the following form. But now the point is that this integral is actually divergent. You can easily convince yourself that this integral is divergent unless these deltas, they take the following form. Okay, where this lambda is basically some arbitrary real number. So these deltas have to take the form 1 plus I lambda if this integral has to converge. Okay, so now these values of delta I, which are of this form 1 plus I lambda, are what are referred to as unitary principal continuous series representations of the Lorentz group. Okay, and this and if you follow the CFT literature, then you know that these sort of representations are actually quite useful in the study of ordinary conformal field theories as well, and they appear in various places. For example, when you try to do let's say like a partial wave decomposition and and so on. So so in standard CFTs also these sort of representations they turn up quite frequently. But the point, yes, yeah.
So the point about the divergence of this omega integral in the inner product. So I'm a bit confused. Is this are you making a statement about the normalizability of these states?
Exactly. But, I'm making a statement about normalizability.
So then my question is that when we usually use scattering amplitudes in terms of plane waves, external plane waves, plane waves are not normalizable.
Yeah,
that's not a problem. I mean, we don't think of that as a problem, right? Because we usually
no. But the thing is that but the thing is that plane waves are delta function normalizable. So in this case, I'm saying that if this integral diverges, then this basis of states are not even delta function normalizable.
Oh, okay. I see. Okay. So the difference is that there's this. So in the usual plane wave stuff, it is normalizable in the sense that you get these Okay, it's in terms of I see. I understand.
Exactly.
Thanks. Okay, great.
Right. Yeah, right. So basically, then, as we just said, is that the statement? So as Madhu pointed out, is that basically if these deltas take this form, then the states in this conformal basis, the single particle states in this conformal basis, will be normalizable, will be delta function normalizable states, and that can be explicitly seen, because if you just put in this form of the deltas 1 plus I lambda and 1 plus I lambda 2, then there is a there is a typo here. This should be -1. So then you can use this formula for this integral, and this basically gives you a delta function which enforces this lambda 1 to be equal to minus of lambda 2. And therefore, what you finally get is that basically the inner product between this conformal basis states that takes the following form. Okay. So so now actually notice from this.
Sorry, I have another question now.
Yes,
So I was wondering this green box on the screen now.
Right.
If I have any integral transform, would it not give me some answer like this?
if you have any integral transform.
If I take the original states I started out with, and then I do any integral, like let's say, can you scroll back up to the definition of the Mellin transform?
Yes.
So instead of writing this d omega delta minus 1, if over there I said just d omega k omega prime, whatever, something like that. So there is some kernel. Okay.
Yeah. Right. Right.
Then I would. Isn't it true that if I,
but the
for
point
a very
is that,
large class of kernels, I will still have some orthogonality relationship, right?
No, so that so that is not obvious, right? I mean, if you take an arbitrary kernel here, then that kernel has to be a very special kernel, right? That kernel has to satisfy some orthogonality properties.
Yeah. So I'm saying you take an orthogonal kernel.
So
of which there are many. So
so basically, so you can do that, but the point is that there is another sort of restriction that we want to put on it, which is that we want these states to transform under Lorentz transformations. We want this to have nice transformation properties. So the point is that whatever kernel you choose, that kernel has to transform covariantly under has to transform covariantly under SL2C as well.
Okay, so the requirement of good SL2Z weight,
that's right,
essentially fixes it uniquely to Mellin.
That essentially fixes this uniquely. Exactly.
Okay, thanks.
Good. Great. So that is so that is what we see. Okay, so from this inner product, I wanted to make a comment about this. So basically, you see that this inner product is basically like a 2-point function, right? So this inner product, if you write this, okay, so this inner product is basically a 2-point function in the celestial CFT, okay, between two operators, right? But then you see that the 2-point function in the celestial CFT generically actually has this form, right? But you immediately notice that there is something very funny about this, because although you can check that this has the correct sort of conformal transformation properties under the SL2C group, but the point is that we never see actually 2-point functions when we study CFTs. We never see 2-point functions like this. All 2-point functions are actually just power laws, right? But in this case, we see that this 2-point function is in a sense ultra local, in the sense that there is this delta function which forces the Z insertions to be the same. And moreover, if you look at the dependence of the and moreover, if you look at the dependence of this 2-point function on the scaling dimensions, which are related to this lambdas and lambda 1 and lambda 2, and then because of this delta function, what you also have is that the dependence on the scaling dimensions is also distributional. So therefore 2-point functions in this celestial CFT will not take the standard form, and they will and so they will be actually sort of more complicated distributions of this form. Okay, so that's one feature which tells you that whatever this celestial conformal field theory is, it cannot be actually just a it cannot be just a standard garden variety to CFT.
Can you repeat the comment about the scaling dimension? I didn't quite understand.
Yes. So basically, you know that in a standard 2D CFT, the 2-point function takes some power law form like this, right?
Right.
Z12 to the power, let's say, some 2 delta, right? Right. So in that case, you don't get any funny delta functions and so on. So the point is that whenever you see an object which has delta functions in it, then that has to be understood in the sense of being a distribution, right? If you want to make sense of it completely rigorously, then you have to integrate it with respect to some test functions and so on. So basically that is the comment that I wanted to make. I just wanted to draw and sort of I wanted to point out what is the difference between the standard standard CFTs and this celestial CFTs, and this is one of many differences which we will see.
Okay.
So the origin of this delta function difference is really in the momentum conservation, right?
It is, yeah, exactly. That is true.
So if we go through the steps up till now,
right.
But if like in the usual study of scattering amplitudes, for example, it is quite common to strip off the delta function, momentum conserving delta function from the amplitude, right?
Yes.
So I was wondering if what would happen in that case. Is that possible? And if not, why?
So basically in this case, so in this case, when we so in a second we will talk about so in a second we'll talk about the integral transform of the scattering amplitude, which will define for us the celestial amplitude as it is called. But as you said, that usually we sort of strip off and this momentum conserving delta functions. It is always assumed that everything we have is on shell, and we never write this delta function explicitly.
Right.
But the point is that the point is that this celestial amplitude is just given by an is by definition given by an overlap is given by an overlap of these asymptotic states, and that overlap by definition actually contains the delta function in it. And those delta functions are sort of and those momentum conserving delta functions are important, because without those you will not get actually the conformal transformation property that you want.
No, but even an ordinary S matrix is an overlap, right? Between an initial state and a final state.
In that case, so in that case, what we usually do is that basically we strip off the delta function, we strip off the overall sort of delta function, and we usually work with the scattering amplitude, right? Which is the object which you are left with when you strip off the delta function. But here I'm talking about the full S matrix element, and the point is that the way I'm going to define it, I'm going to define my celestial CFT correlator as being an integral transform of the full S matrix element. And that will be and that is important to do, because otherwise whatever I try to define as the CFT correlation function will not transform as a CFT correlation function.
Okay, but okay, fine. Sorry, I just give me a second. So like what if I was not so insistent on it transforming like a CFT correlation function, but I did the stripping off of the momentum delta. What would I get then? Is that something that people have seen?
So yes. For example, that of course one can do. So that of course one can do. Actually in certain actually in some cases but well, I can't actually think of but in this case the thing that we want to do is that we want to sort of bring this underlying conformal symmetry sort of to the front and make it manifest.
Right.
So for that purpose, it is important to give the delta function.
Sure.
But
okay.
What you could do is that you could define a more but what you could do is that you could obviously define a certain mathematical object, which would be an integral transform of just a stripped scattering amplitude, which doesn't have the delta function in it, and that in itself may be a well-defined mathematical object, but I don't know if that will have some interesting physical.
Maybe we can talk about it later. Sorry.
Sure.
Can I also ask a question? So I'm a bit confused. So in the usual CFT, the only assumptions that you put is that these are conformal primaries and they transform under global SL2C, and you get this power law behavior. And whereas here I'm doing some construction and I don't get this power law behavior. And isn't this in contradiction with each other? I mean, either the so here the only ingredient that has gone is
so that is
that has gone is the state operator. I mean, until the green box, everything is fine. that is just the inner product on some states, and then you interpret this as a two-point correlation function.
Yes.
So why and you're still calling these operators or also as primaries, and it doesn't it seem to be contradictory? Am I missing something? I'm not sure.
No. So in that case, that is actually not contradictory, because the point is that so basically the point is that so basically the point is that if you just insist on conformal invariance, then in that case conformal invariance does not quite tell you that it has to be a power law, right? I mean, there are other functions which you can write down which will also be conformally actually sort of covariant. But in the standard discussion of quantum field theory, what we or in CFT, another sort of thing that you impose is sort of actually locality, right? That as you take things far apart, then things fall off at a certain rate and so on, right? So that motivates us to choose a power law ansatz. And then what conformal symmetry does is that it basically tells you that the scaling dimensions of the two operators have to be the same. So if that does not happen, then the 2-point function vanishes. But the point is that there could be other forms of the 2-point function which would be consistent, which could be consistent with conformal invariance, but not with the standard notions of locality.
I see.
Good.
But Sudip, I thought that the scaling property is what gives the power law behavior, right? In CFTs, like a field has a scaling dimension, and for that you have this Z12 to the power delta. Is that wrong?
No, that is correct, but that is also satisfied by
So for example, for example, what would an alternative definition of O1, O2 2-point function be?
Within a CFT, I think he's asking.
Oh yeah. Oh yes. So So for example, okay. So maybe one thing which I can say is that yes. So for example, in this case also, if you take this form of the 2-point function, which is what we get from the inner product of these states, then in that case you can check that it has all the nice conformal transformation properties that you want a CFT 2-point function to have. But the point is that usually these sort of 2-point functions usually don't arise in the case of standard local quantum field theories, right? And there is an inherent assumption of locality that goes in. But actually what it turns out is that in this celestial CFT, if you compute the 2-point function between an operator and its shadow, let's say call it O delta, then that object has the standard 2D CFT form. Sorry, this is a bit too long. Yeah. So if you compute in celestial CFT, if you compute 2-point function between an operator and its shadow transform, then you find that it has the standard power law behavior, but not if you just compute the 2-point function of two ordinary operators.
Shubham, I mean, so one is in relation to something that Shubham and Subbu were asking. But
sure.
I think is the point you're making that if you in addition to requiring that our S matrix elements are unitary and S matrix is unitary and stuff like that, we also require cluster decomposition in usual quantum field theories, right?
That is true.
Which means that if I take the points apart, then the S matrix element should vanish. Like if I take them far apart.
That is true.
So if you're saying that if you just impose a unitarity of the S matrix, if you don't impose cluster decomposition, you get a larger class of possible functional dependencies, and it is sort okay. I see.
Yeah, exactly.
No, but I mean,
no, but in this case, it's just very ultra local. So you should still have for the delta function.
So
You should
in this case,
this
is
So
in this case, it's ultra local, and it is also ultra local because this sort of thing lives at null infinity, right? where basically the metric also degenerates. I mean, at null infinity there is no Poincare invariant metric. So yeah.
Other examples like log,
right,
and so on, those would satisfy maybe conformality, but violate cluster decomposition.
Right.
But there are other functions which does this. It's not as
that's right.
I mean, in fact, I mean, ultra local, it's so bad that you can't move the points.
Exactly.
Right? So,
Exactly.
Damn weird.
Exactly. Yeah. So it is just saying that one die sits on top of the other. So the point is that this makes complete sense from. I mean, this is not funny from the point of view of the bulk space-time picture, but this is funny nonetheless from the CFT perspective.
Sudip. Sorry, I had some random quarantine thing, so I had to run. But let me just, if this was discussed. So this form, is it related to this delta being taken to be complex? So delta is.
No. So the So in this case, okay. So although we started with this deltas.
Right.
What you can, at the end of the day, you can, once you get this answer, you can analytically continue and get other values of delta from this.
Okay, let me phrase it differently. So what is the scaling dimension of this O1 and O2 now? Is it delta or is it delta or lambda?
So the scaling dimension is 1 plus I lambda 1. And 1 plus I lambda 2.
Okay, so scaling dimension is complex. Okay.
Yes, the scaling dimension is complex.
Okay.
And in this case, one of the points about this celestial conformal field theory is that in this case, it turns out, so another thing is that it turns out that this set of conformal dimensions conformal dimensions of this form, which lie on the principal series, on the so-called principal continuous series, are at the end of the day not the most general things that we want. So for example, as we will see, is that for many purposes, especially for studying the operator product expansion, we will see that we need to augment this principal series, and we need to consider scaling dimensions which can take arbitrary complex values, and which are not just restricted to sort of this form 1 plus I lambda.
I see. Okay, thanks.
So actually, guys, by the way, how am I doing for time?
I think we're up on an hour and a half.
Okay. Okay.
So I don't know if that's really bad.
Actually, how long do you actually go on?
So we usually go for an hour and a half, and then of course plus minus a little bit. So.
Okay. So maybe So in that case, do you want to actually sort of continue this next time? I mean, I don't want to rush over things.
Would this be a natural stopping point?
Yeah, I think it would be a natural stopping point, because after this we will sort of see, we will just check whether it has the correct sort of conformal transformation property and so on.
I see. Okay, I think that sounds good. Maybe we can just have questions, since people seem to have a lot of questions.
Yeah, sure. Please go ahead. Okay, so I will just stop there.
Okay. Questions, anyone?
Like usually, like there is some literature on like taking flat space limit of CFT correlators.
Yes.
I was just wondering, like if many of the operations seem like similar to this thing. So I was just wondering, like, if you would be
similar in what sense? You are saying that there is also this Mellin amplitude.
Yeah, like, well, I mean, usually, like, you take a plane wave representation, like usually a bulk to boundary propagator, say for the scalars is of the form 1 by the bulk point distance between the bulk and boundary point to the power delta, say something, and then you can like write a plane wave representation of that form, like, which essentially is like that omega to the power delta minus 1 times a plane wave, basically. E to the power I is a Schwinger parameterized Schwinger representation.
Yes, I know what you're talking about.
So that's why I just asked, like, the massless and the massive case, you are saying that they will be qualitatively different. Whereas for the flat space limit that I am familiar with, it's not. At least for scalars. Now, I was just wondering, like, I mean, looks like I was thinking something to be correct, but at that point it was just that it's perhaps not similar. So
so basically there are some formal similarity. There are some similarities in the sense that, I mean, when you take this flat space limit of ADS CFT, it is usually, I mean, the best way to do it is by considering this Witten diagrams in Mellin space, and then taking, because in the flat space limit, you know that this that basically this in that case, this Mellin variables just become the Mandel-Stein invariants in the flat space limit.
Correct.
So basically that one can do. So in that sense, there is some formal similarity. But you could ask the question that can we actually get what we want to get at? Let's say like a holographic description of quantum gravity in flat space by taking the flat space limit of ADS CFT, right?
But people have recovered like flat space scattering amplitudes from such an exercise, right?
Right. But I think actually there are various. I mean, I may be wrong, but what I sort of felt is that there are actually various subtleties in that. In the sense that, for example, there are all these asymptotic symmetries, right? So by taking just the flat space limit of ADS, does one recover all these asymptotic symmetries of Minkowski spacetime, because the boundary conditions are very different and all that. So.
Well, I mean, I would say that the flat space limit is basically like so in the usual picture, what happens is that, like, you have very high energy particles pumped in from the boundary of ADS from the Minkowski cylinder, so that, like, they don't see the curvature of ADS. So actually the scattering process is appearing in a very local small patch of the ADS bulk. So, like, for all practical purposes, that is like a Minkowski space patch. Now you're saying that, like, like, I mean, isn't like if I take a local patch of very small local patch of ADS, like, I mean, you're saying
right.
that.
So I understand your point, but the thing which I'm skeptic about is that whether you recovered, the object that you get in the flat space limit, whether you recovered, whether you, okay, so so I'm saying this, I'm sort of bringing this asymptotic symmetries into the game here, because what turns out is that in order to understand the various properties of this celestial conformal field theory, it is actually important to understand the constraints of these asymptotic symmetries, because all these asymptotic symmetries, they take the form of word identities of certain current algebras.
I mean, it seems to me like there is like there are two viewpoints in literature. Like I'm just like one where you start from a CFT and get at something. The other point is that you start from the flat space scattering amplitude and try to get at the CFT. Both of these seem to have like problems, but you're saying that, okay, I see. I don't know, in the first picture, that one I am familiar with, whether someone has tried to look at this from this issue, that if you take the flat space limit of the ADS in the this thing, whether one recovers the asymptotic symmetries.
So
they certainly recover, like, given some Witten diagrams, they certainly can give
recover
you
the S matrix.
the S matrix, flat space S matrix. That's for sure. Like there are papers where they do that. Even like I think you have even graviton exchange also has been done. Yes, exactly. Gary Giddings and Penadon. So I was just wondering, like, somehow that seems it's the work of Strominger et al. Suggests that that route will not lead you to something coherent, what you would call a S matrix.
So in this Strominger's, so well, actually, one of the things is that actually this business of asymptotic symmetries is a bit thorny in the sense that I mean, often, actually, one. I mean, what constitutes an asymptotic symmetry is sort of depends on one's choice, because there are various sort of, you can impose different boundary conditions according to your wish, and you could consider one set of asymptotic symmetries as being valid and the others not being valid. So so that is there. But what I have, I mean, honestly speaking, I'm not an expert on this, but what I've heard from, I mean, people giving talks like Strominger and all. So what they seem to be suggesting is that that this program of, or just the naive thing where you take the high energy limit, so where you take the flat space limit of ADS-CFT, that does not reproduce. Okay, so for example, you could ask that that if you, let's say, you consider some gravitational scattering in ADS, okay, and then you take the flat space limit of that. So then in the flat space limit, can you reproduce, let's say, this BMS super translations? So what Strominger and others claim is that no, you cannot do that. Well, in a certain sense, nobody has actually done it. I mean, there is no proof that it cannot be done, but certainly no one has done it.
I see.
Mm-hmm.
Well, I mean, like the fact that I will be able to give you a prescription between CFT CFT variables and the flat space H matrix that you are familiar with. Like, so for example, what I'm saying is that following that, like, given a if I my understanding of the formalism is at this place that given the flat space amplitude, I can tell you like the correlator from which you have derived, like I can tell you like this thing that you have derived.
That is true. That is
but
true.
you are saying that in order to fully say that this is flat space holography, there are some additional things which you need to prove, and which have not been done as of yet. But nobody is saying that they can't be done.
Exactly.
I see. Okay. And this is the flat space, the reproducing the BMS symmetries from Penedonis like approach, like something.
So basically, I mean, the basic point is that whatever be the holographic dual of quantum gravity in flat space, it better have this symmetries. I mean, the symmetries between the bulk and boundary should match. So in this case, the problem is that this is sort of the inverse of what we do in ADS-CFT, right? Because in ADS-CFT, at least we have a concrete example of an independently defined sort of theory which lives on the boundary, and we know what are the rules of the game. But in this case, the problem is there. And also, actually, one of the other points is that as we will see, is that whatever be this conformal field theory dual of sort of flat space quantum gravity, that cannot be a garden variety sort of CFT. Like one example we just saw, right? That 2-point functions take a very funny form and so on. And then these are constrained by infinite dimensional symmetries and so on. So one has to actually see whether these infinite dimensional symmetries get reproduced once you take the flat space.
Well, I mean, I was thinking that like in this 2-point function that you were writing down, you were just getting some support on the light cone, because essentially what you were localizing,
getting support on exactly.
Just and if I am not wrong, similar kind of things happen for like if you try to compute like a 2-point scattering in the Penedonis approach also, like there seems to be, like, I don't remember like this calculation, like
okay, I might have to look at that.
So that's why I was just asking, very curious about this, like, because there were a lot of similarities which seem to suggest that this was there, but maybe I also need to look at it. But certainly people, I don't think people have even progressed along this line, that in the usual sense of flat space limit of ADS CFT, whether you recover BMS symmetries. At least the Penedonus group of thinking have not explored this.
So basically that seems to be the status. I mean, from what I hear from people is that that this program, I mean, so that has, as you said, that this has never been sort of done fruitfully, and whether the asymptotic symmetries which are related to soft clearance and all, whether they are correctly reproduced in the flat space limit, that is not known.
I see. Thanks a lot. I must have taken you way off route.
No. So in this case, it is actually so it is more fruitful to have a discussion than just me sort of blabbering on for 1 hour.
All right.
So Sudip, I have a question. I think it's related to what's happening in the chat right now. So
I see. Actually,
there's a lot. I mean, there's a lot of things. But this is a question from slightly earlier. The question is, if in 2 dimensions, Nirmalya pointed out that in 2 dimensions, if I just take like scalar fields, right, and I compute the 2-point function of a scalar field in 2 dimensions, then it turns out to be delta function. It turns out you get a delta function.
2-point function
in two dimensions.
No, I was saying that if you don't log, right? if you don't normalize the fields or something, then you get a delta function. Otherwise, you get a log. But if you just leave out the 1 over omega piece, just take e to the power I omega x minus t, and then
so basically
somehow
I'm
looking at some
you construct these vertex operators, and the vertex operators have the standard sort of 2-point function, but the ordinary field which appears in Lagrangian has this logarithm.
So my question is that, like, in this case, in the case of the celestial CFT, there's 2 questions. The first question is, in the case of the celestial CFT, it looks like the 2-point function is a delta function, right? Now, my question is there some function of the states that you've constructed that would look like a usual power law kind of thing? Like,
yes. So
some sense, like I'm saying that, like something like a vertex operator, but not exactly the same, because
well, certainly if you take a shadow transform, then as I said, that the 2-point function of an ordinary operator and the shadow in the celestial CFT, that has the standard power law form actually. So in that sense, it is in that sense you are doing a sort of convolution, because the shadow transform involves integrating against, you integrate the operator against some function.
So then that brings me to the second question, which is that in the case of the shadow, so maybe that I mean, in some sense, like there's creation and annihilation operator, so then there's the operator and then it's shadow.
Exactly.
Right. So maybe when you're computing correlation functions, then the objects to look at are not the ones where you just have like operator, but then equal number of operators and shadows of those operators or something.
So yes. So actually that you can do, but as you said that so basically what we will do actually next time. So basically what we will do is that we will think of not in terms of this basis states, this one particle states, but it is more useful to think of so as you said, it is more useful to think of in terms of creation and annihilation operators,
right?
And those creation and annihilation operators will be or the Mellin transform of the standard Fock space creation and annihilation operators will be my dual CFT primary operators actually.
I see. Okay.
And you take those operators and you compute their correlation functions. That is the Mellin transform of the S matrix.
I see. Okay. All right.
So Sudip,
I will try to read the questions in the chat at some point. Sorry, I didn't read it.
So Sudip,
yes, go on, please.
So the 2-point function, as you said, because of the delta function, it does transform, like it does satisfy all the conformal properties.
Right.
But can we read off from that expression what the conformal dimension of the corresponding object is? Is it H or?
Yeah. So from that you can of course read it off. Yeah, so basically, if you try to actually take that form and you try to do the SL2C transformation, you will see that it transforms in the standard way where, yeah, from that you can read off the HH part. Yeah, so basically H, yeah, as you know that H is just delta plus sigma by 2. So delta in this case is 1 plus I lambda, say, and sigma is whatever, some integer number. Yeah, so H will be, yeah, so H will be 1 plus I lambda. 1 plus I lambda plus sigma by 2, and H bar is 1 plus I lambda minus sigma by 2. Yeah. And that you can read off from the transformation.
Read off from the transformation.
Yeah.
Sorry, I mean, I'll just ask one last thing about this thing. So in higher, in 4D, for example, 4D CFT, we only have the global conformal group, right?
That's right.
So then suppose I wanted to get a delta function of the position of the fields for the 2-point function, and I wanted the scaling dimension to be real. That would not be possible. Is that correct, or is that still possible?
No, sorry. So let me understand. So yeah. So what you want? So can you just say again what you wanted to do?
Okay, I want two fields, O1 of x1, O2 of x2.
Okay.
And
these fields are in 2D CFT or
4D? 4D. Yeah.
Okay.
Yeah, 4D. So there is the global conformal group. So the argument I usually know is that the Lorentz invariant says you need to have the, I mean, translation invariant says x1 minus x2, Lorentz invariant says mod of x1 minus x2, and then 1 by something, right?
Exactly.
So suppose I want to, but could I also take the delta function and keep the scaling dimension real?
Yeah, that, well, yeah, I mean, in principle, you could do that, but yeah, but that will not, yeah, but that we usually don't do, as we said, because of the standard sort of assumptions about locality that we use in quantum field theory.
I see.
Yeah. I mean, in this case, you are getting this localized support on the light cone because of the fact that if this object really lives on null infinity, then there is no Poincare invariant. I mean, the metric is just sort of degenerate, right?
Right.
On the sphere. So in this case, the metric is degenerate at null infinity, and then you can't write. Yeah, so that forces you to only one possible thing, which is this delta function.
Okay, but just focusing on global conformal invariant, suppose I wanted a scaling dimension delta, right?
Yeah.
What delta function of what would I write? Okay, I won't call both of them delta. Okay, let's say h. So
let's say h. Okay.
What delta function would I write of x1 minus x2?
What delta function would you write?
Okay, something like a delta of x1 minus x2 mod to the power.
Yeah, something like that. Yeah.
I see.
Yeah, that will of course be rotationally invariant and translationally invariant.
Okay.
But now you have to check. Yeah, but maybe that will not be. Yeah.
Yeah, scaling also would work, I think, because
scaling also would work.
Scaling also works. Yeah.
Okay.
Some
just comes
ultra
out of
local
the
thing.
data.
That's, I think.
Okay, great. Okay, sure. Okay, thanks. Yeah.
Any further questions? Okay, if there are no further questions, let us thank Sudip for today's excellent talk.
Thanks, Sudip.
Hey, yeah, no problem.